Hello, everybody. So then in this particular sequence of videos, we're going to talk about the determinant in general. This is where the course becomes fairly abstract, or starts to be. Because of that, I'm going to lean a lot more into proofs in order to try to nail down what's happening. If I don't do such a thing, very quickly, it'll just become a collection of facts that you'll just have to believe. So I need to argue it so you understand where things come from. So in order to do such a thing, first thing is that you might recall that for 2x2 matrices, that we already have a way to associate an eigenvalue with a certain type of determinant. If lambda is an eigenvalue, that means there has to be a non-trivial vector to the null space of A minus lambda times I. But that means in the matrix, A minus lambda times I is not invertible. And we know for 2x2 matrices that that means its determinant is 0. We really need to go and find a way to extend that result. But that means we need to define what we mean by a determinant for a 3x3 or 4x4 or 5x5 and so on. And then once we have this new function, because it's going to take a matrix and associate to that matrix a number, what kind of properties does it have? What kind of algebraic property does it have? So first, we'll review a little bit. So the 2x2 determinant is not going to change, exactly the same as before. So what you do is you take the product along the diagonals. I do the products in this order. So if you take the positive entries above and take the negative entries below, to subtract them, that would be the determinant. So finding this particular determinant is really easy. This would then just be equal to 2 times 5 minus -1 times 3, which of course is a 13. Now, the nice thing is that for 3x3 matrices, we can actually kind of get the same thing. We can use the same kind of trick. To do that, though, I need more entries. So the typical way to do a 3x3 determinant, if you're going to use this method, is to take the first two columns and just copy them over and put them to the right of the matrix, like this. And then working from below, going from right to left, going up diagonally, you get all those products and add them together. That will be P. And then going from top down, again, right to left, you go along diagonals and get all those products and add those together. That sum of products will then be called N. The determinant then is just the difference of those sum of products. So doing it here is really easy. I'll do it by once. So I'll just take that matrix. I make another copy of it. I take the products going up diagonally from right to left. And I take the products going from right to left, going downwards. The top one's P, the bottom one's N. So the determinant then is just 3, the subtraction of those two numbers. The problem is this doesn't work anymore. So we can't use this idea to generalize how to find determinants of 4x4s, 5x5, 6x6s. Now it's interesting that determinants, the idea of a determinant, actually came about before the idea of matrices and products and addition of matrices. All the idea of a determinant came before all that. So it's actually interesting that in the end, there's this nice interplay between the way we define multiplication and the way we define determinants. So in order to figure out another way to look at our determinants of our 3x3 matrices, here's that exact same sum of products all over again. I'm just going to notice that if you take that and reorder it like that, so then if you multiply that out, you get the same as the original sum and differences of products. But each of the expressions in parentheses are actually their own determinants. They're just determinants of 2x2s. That's that. In fact, notice what's happened is that along the first row, that's right here, I took the entries of that row, and then for each of those entries, I then took that entry and I wiped out the row and the column. What's left over is a 2x2. So just so you can see what I mean, look at this matrix right here. Take A, and I want you to wipe out the row and column. Do you see how you get the matrix right there? It's neat, right? And the products are added and then subtracted in successive order. So plus, minus, plus, minus, plus, minus. This is how we will go and extend determinants to higher size matrices. So just to see how it's done again, just make sure you understand. So if you take the matrix I got for you, 1, 2, 4, 0, 3, 4, 2, 1, 5, then what you see here is expansion along the first row. It's called the cofactor expansion along the first row. So I have 1, I had 2, and I have 4. Notice how it goes plus, minus, plus. And if you want to know the corresponding determinant of the 2 by 2 that I have to multiply to these numbers, for each of these numbers, just go to that number in the matrix and wipe out the row in the column. So let's see 2, for example. So I should get the matrix 0, 4, 2, 5. So take 2 and wipe out the row and the column, and there it is, 0, 4, 2, 5. Neat, right? Now, what's actually really neat, is that when you find this determinant, we get, of course, the same answer we got before. But we can use this idea to define the determinant in general by expanding on any row or any column. To do so, you need to know certain terms that are corresponding or that correspond to the objects I've been creating. So look at this matrix. Suppose you take the first row and the first column and wipe them out. You'll get a matrix. We need a name for it. So if the original matrix is called 1A, then the new matrix would be the matrix A sub 1, 1 for wipe out first row, first column. So A sub 1, 1 means take the matrix A and just wipe out the first row, first column. And the resulting matrix is the matrix A 1, 1. Now, so in general, the matrix A sub ij is the matrix A where you wipe out the ith row and the jth column. For that matrix, it will have a determinant. We'll call that the minor. So the ith jth minor of A is the determinant of the matrix after you get rid of the ith row and the jth column. But then in the determinant, there's this plus minus, there's this oscillating sum. So we call that the cofactor. So the cofactor is actually the minor, but multiplied to a power of -1. And the power on -1 is the sum of the I and j. That way it's guaranteed to go plus minus in the summation. So the C sub ij is the ith jth cofactor of A, and it's a number. The ith jth minor is a number. A sub ij, that's a determinant, that's a matrix. Let's just make sure you understand what I mean. So then here's this matrix. I want to know what is A sub 1, 2. I want to know its minor. I want to know its cofactor. So for A sub 1, 2, that means first row, second column. So get rid of first row, get rid of second column. And then the resulting matrix is 0, 4, 2, 5. The minor is just the determinant of that thing. So that would then be 0 minus 8, which is, of course, -8. The cofactor is -1 to a power, the power being the sum of the I and j. So that's 1 plus 2 is 3, times the minor. So that would then be -1 times -8. The answer, therefore, is 8. That's the cofactor. Okay. Now that you have that, we can then define what we mean in general for the determinant of a matrix. It's done by using this theorem. This is not a theorem we're proving. It would require induction, and in the textbook, I think it's like a page of work. It's just not worth our time to do so. Instead, I'm just going to state it, and then if you ever go on and go to grad level work, you probably will come back and prove this anyway. So if you ever form the cofactor expansion along the ith row, or the cofactor expansion along the jth column, you always get the same number. That's what's really neat. So since it's always the same number, we'll give it a name. It's called the determinant of the matrix. So you can find the cofactor expansion along any row, any column. You will always get the same answer, and we call that the determinant. I just want to show you how to do it by hand at least twice. So look at this matrix. 1, 2, 4, 0, 3, 4, 2, 1, 5. And let's find the cofactor expansion along the first row. Let's find the second column cofactor expansion also. Now, when you find the cofactors, it's sometimes a pain to deal with the -1 to a power. Just notice that the cofactors the sign that goes with it corresponds to this grid that I have right here. So the first row, first column cofactor would have a plus in front of it. The second row, first column cofactor would have a minus in front of it. That way it's easy to remember. So once you have the first sign, plus minus, it's easy to get the rest. So along the first row, I'm going to be using these entries. So that would then be 1 times C11. Then I have plus 2 times C12. Didn't mean to do that. Times C12. And then I add on to that to get 4 times C13. So that is 1 times. Now C11, that's plus, so I have a plus there. And then I need the determinant of the corresponding matrix, A11. I need the minor. So if I look at the first row, first column, and wipe them out, I get 3, 4, 1, 5. After this, everything, all the cofactors just oscillate. So then in sign. So the next is minus then. Minus 2, determinant of the corresponding matrix. So then I need A12. So take first row, first column, wipe them out. You get the matrix 0, 4, 2, 5. Then we have plus, because it's oscillating sign. Then you have 4, and then the minor. So for 4, I wipe out first row, third column. I get 0, 3, 2, 1. So that would then equal 1. I'd have 3 times 5 minus 4. That's 11. Minus 2 times. I get a minus 8. 0 minus an 8. So that's minus 8. And then I have plus 4 times. And I get minus 6. Minus 6. So just add that up. See what the answer would be. So I have a 16 plus 11. That's 27. But I'm subtracting 24. So that's 3. All right, good. So let's do it again. Now let's go do the second column cofactor expansion. So then I'm going along this column. So I have 2, and then the cofactor for the first row, second column, plus 3, then the cofactor for the second row, second column, then plus 1 times the cofactor of the third row, second column. All I gotta do is figure out what those are. So that equals 2. Now the cofactor for the first row, first column, first row, second column starts with a negative. See, it's a negative. You see it right here in the picture. So that's negative. Then I need the minor. So take the first row, second column, wipe them out. You get the determinant of 0, 4, 2, 5. Next, we'll have happy plus because they oscillate. Then you have 3, and I need the cofactor for the second row, second column. Wipe me out, second row, second column, take the determinant, gives me 1, 4, 2, 5. Then I have last 1, that's minus 1 because the signs oscillate, minus 1. And then I wipe out, in this case, the third row, second column. So third row, second column, I'm left over with the determinant 1, 4, 0, 4. All right, let's just bash out those numbers. So that would then be negative 2 times negative 8. I would have plus 3 times 5 minus 8. So 5 minus 8, that's negative 3. And then I have minus 1 times 4. So let's see what that would be. You'd have negative 2 times negative 8, 16. Negative 3 times negative times 3 is negative 9. I have minus 4. So I have 16 minus 9 minus 4, and you get 3. Yeah, that's right. So there you go. This will be the definition of the determinant. It's done recursively so that you can find the determinant of any size matrix. A 4x4 becomes a whole bunch of 3x3s. The 3x3s become a whole lot of 2x2s, and so on. So clearly, though, while this is a definition, we never want to do this. We never want to do this. So we need better techniques. We need better techniques to compute determinants. And that's what the next sequence of videos is all about. I think it's enough for this one.